to be able to have a good feeling that the shaft is drilled properly at the right angle, that there is no necking, and to have good quality control, knowing that the bottom of the shaft is absolutely clean, before you fill it with concrete. Very, very useful information for the drill shaft industry. Like I said, 10, 15 years ago, I knew a few engineers that admitted to me, no way will I use a drill shaft. I don't have enough faith in it.
Right. I remember
it's
that.
a totally different view now, totally different view.
I'm Kevin Lathan, Construction E-Link and Omega Trestle. We're experts in temporary trestle. So I know a little bit about this, but I'm always wanting to learn more.
Well, Kevin, first of all, thank you for giving myself and I'm this opportunity. Thanks to PileBuck also. Hopefully, in the next 30 minutes or so, we'll be able to, as you say, inspire at least one person. So
that's a goal. What do you do? What's a typical day at GRL Engineers?
Basically, GRL is a geotechnical engineering company specializing in deep foundation testing services. That's what we do. Historically, our company, together with Pile Dynamics, have developed many geotechnical testing devices that are used in the industry to better deep foundation elements. I guess maybe quickly a little history of our company. It's really, I always thought it's a cool history. I've been with the company since I was fresh out of college, 7 years or so ago. This testing method here, started in the 60s at a university, Case Western Reserve University.
Excellent institution. Excellent.
Yeah, yes. At that time, that's right. That's what it was called. Dr. Goebel, a professor, and two of his graduate students, Frank Rauscher and Garvin Likens, by the way, who are obviously the GVR and Yale in the company, embarked, I guess, on a mission at that time. They thought, is there a quicker, cheaper way to determine the capacity of a driven pile relative to the old-fashioned way that it was, how it was tested, of course, which required the use of a static test, loading the pile with either weights at that time, which was very expensive and very time-consuming, of course. So that was their mission. Well, I don't know, 10 or so years later, they incorporated into GRL. They had a working test method, called it dynamic pile testing, using the pile driving analyzer. And that's the history. Today, our GRL Engineers continues to expand its capabilities for both, driven piles and, of course, drilled shafts, which I think over the last decade or so have been used more so than they used to be anyway.
Yeah,
so a little bit about our company.
No, it's beautiful, and I understand that the science of it was basically looking at the math of springs and the wave movement of energy and correlating that to the old-fashioned way, which was, hey, we know that a pile driven with a certain amount of load and receives a certain amount of resistance, we would correlate that with the static load test. Or now there's dynamic load tests, but they were expensive. They took a lot of time. I've spent a lot of time as a young engineer out in the middle of rivers, and it was days, weeks, and so now it's done in minutes. And you're finding that correlation still stands true. That the technology of adding as I recall, it was a accelerometer and a transducer to pick up these energy waves, bouncing down to the tip of the pile, reflecting up, measuring the time, and then putting it through the the mathematical spring models. That's still solid to this day. Is that true?
Oh, of course. I think it's even more solid as you say. You know, both GRL and Power Dynamics strive to make these methods better, more reliable with you know, more correlation studies. And so, yeah, we've gotten better over the years for sure.
Yeah, no, that's great to know that it continues to get fine tuned, and now you're moving into the drilled shafts. So there's a menu where it started with the driven pile, and you have a kind of a number of different services that you're offering now, and what are those?
Well, it's a long list, really. You know, I mean, historically, of course, the company was, you know, dynamic testing of driven piles. That's the way the company was started. Today, we are involved with many tests for the driven for dynamic testing. Of course, can be done both on driven piles and also drilled shafts. We also do static load testing. I mean, you know, even though it's more expensive and more time consuming, it's still done on a routine basis. So we're still heavily involved with that. When it comes to drilled shafts, people are interested, clients are interested more in really in integrity and reliability of the shafts. So there's, I don't know, half a dozen tests or so: cross-hole sonic clogging, TIP, the newer one, thermal integrity profiling.
I'm a big fan of this new TIP, the thermal integrity profile.
Yeah, for sure. I mean, for, you know, in every test there's limitations, of course. So, and certainly cross-hole, you know, that what you were describing was the debonding issue,
Right.
which, you know, can happen, and that causes uncertainties. That, you know, is it debonding, or do we have a problem? So yeah, you know, you know, like any other test, there's limitations.
Yeah, but there's new
so,
sleeves, and that's kind of, some of that's gone away, but that's
not really, but it's still there sometimes.
it's been improved.
Yeah, I think, you know, I think some clients have, you know, expressed concerns that sometimes cross-hole sonic logging is a bit too sensitive. You know, it can show something that maybe is concluded that you know, can be, you know, severe or detrimental potentially, and it really may not be. You know, that you know, that they think that the testing method maybe is just a little bit too sensitive. In that respect, thermal integrity profiling, I think, has helped that too. Not that it's not sensitive enough that it, you know, that it'll miss things, but it may miss some little thing, possibly a little tiny inclusion near a tube or something, you know, that CSL may pick up, you know, and potentially show an issue. So, you know, both tests are still very useful. I don't mean to say that one is better than the other. You know, we now have two different ways of testing shafts.
But the shape, I think, is really important too. The where you understand, you know, the shape, so you understand how far it's spreading, because you get a texture kind of profile in the edge. And typical drilled shafts are you know, thought of as just pure end bearing, right, in the math that the engineers do. But there is a friction element when you understand what the external shape is.
Yeah, I mean, with shape, yeah, you get a three-dimensional view of what the drilled hole looks like. You know, and in terms of design of drilled shafts, I mean, some engineers don't want to, for example, depend on end bearing. They just, because they don't want to rely on the end bearing because of the cleanliness potential issue at the base. So they design the shafts all in friction. I think for the most part, most engineers, most designers do that. Over the years, I think some have started to, you know, because of these testing methods, actually use some of the end bearing because they have a better faith that, hey, the bottom is clean and the concrete is definitely bearing on bedrock. So the importance of these two tests now, shape and squid, I think it's helped the industry, the drill shaft industry, in a good way. I think I mentioned it to you in our previous conversation that, and you said it yourself, historically, some designers, engineers wouldn't use shafts because of these uncertainties. But now, they have, they have more faith, and the contractors themselves, of course, at first hesitated using these test methods, but then they realized, hey, you know what? If we can prove to a client that the shape is correct and the bottom is clean, they'll tend to use them more, of course.
And I'm excited that there's testing now on dynamic testing on drilled shafts, because that's I don't know enough about that, but maybe you could explain some of that to me.
Sure. Well, I mean, in terms of the cost effectiveness, certainly when you compare a dynamic test to the old-fashioned static tests, as you say, they don't even compare. Dynamic testing can be performed on several piles in one day. Results are immediate. Recommendations can be given to the contractor immediately, and production driving continues. No delays. Not to talk money, but you're looking at a maybe $3,000 cost to test several piles in a day dynamically. As you probably are aware, a static test is probably going to take you a week by the time you set up the frame and everything, and it's probably going to cost 20 grand. So
easy. We got to remove the frame too, and usually move it to another spot, right? Because the geology in these structures are, whatever, 100 or several thousand feet long, and the geology changes. So it's
sure. So it's really night and day when you're comparing the two tests. More importantly, or just as important, dynamic testing is done throughout the pile driving process from the beginning to end. So not only are you evaluating soil resistance during driving, but you're monitoring driving stresses, both compression and tension, and also evaluating or monitoring the integrity of the pile. So if you ever have some damage, that is clearly evident in the record. So is it cost effective? Extremely. Is it much better than static testing? In many ways.
So we're bouncing back and forth a little bit between drilled shafts and for the young people at home who don't understand the differences. A drilled shaft where we're drilling a hole. We usually put some type of sleeve in there if the geology isn't competent to stand up on itself, and we put a reinforcing steel cage in there and some monitoring devices, and we tremie concrete. We pour it from the bottom up, and we make a shaft. Drilled pile is either a concrete or steel or driven pile, rather, concrete or steel or timber or whatever you want it to be, driven into the ground. And we understand the load capacity of that by how many blows per given foot, per given distance, and knowing the weight of the hammer and those things. So here's a simple analysis that I look at as an engineer. I am a licensed professional engineer, but I'm more of a practical builder. But from what I've seen, though, is the driven pile is typically a friction element. Okay, and I know it's not 100% of the time, but typically I'm saying more than half the time, a friction element, and a drill shaft is more of a end bearing element. And I know that's a real generality, but I think that's true. Okay, and when we're would you say that that's reasonable? I mean, it's not everywhere across the board, but it's
I don't know. I mean, it would be interesting to look at that, because it's really based on the region of the U.S. Obviously,
I get it.
Where you have shallow rock, most often you drive H piles to rock, and you have a lot of end. So, West Virginia, Pennsylvania, New York, yeah, they drive a lot of H-piles to rock in their end bearing. Drilled shafts, you say that they're, in most cases, they're end bearing. I think that's maybe more so today than it used to be, just because, again, designers, engineers didn't trust the end bearing issue with the potential cleanliness of the shaft. Um, Again, if you've got bedrock, yeah, they're going to socket that drilled shaft into the bedrock, and they'll get most of their resistance from actually the friction on the rock socket, and then some end bearing. So I don't know. It's probably, my guess would be it's probably half and half.
Hey, we hope you're enjoying our show, and if you are, we would appreciate it if you would help us out. Crush that like button, hit the subscribe, and be sure notifications are on so you'll be notified whenever we release a new podcast, guide, or compilation. We appreciate the support, and now let's get back to the show.
When you look at how capacity is determined in a dynamic test, right? It's determined, as you say, from this one-dimensional wave mechanics. You hit a pile and you send a compressive wave down, and this compressive wave may encounter some resistance, soil resistance, which then sends up a reflection. And this reflection then returns to the top, and then our strain gauges and our accelerometers detect that. And the key is then to measure the magnitude of that wave. That's what determines the strength of the soil. So the accuracy really is not dependent. The capacity is really determined on how these waves that are input in the pile, how they interact with the soil resistance itself. The accuracy is not really dependent on the magnitude of the soil resistance.
Okay, right. We just drive the pile deeper. That's all. We just keep going till
it's just it's just bigger pile, bigger loads, bigger resistance, bigger capacities.
Right. So that information's all fed into these programs, the CAPWAP and the GRL WEEP. Can you help me understand those better? Because I get a little there's a lot of details there that I don't fully understand, and I'd like to. Could you simplify that for me, please?
Yeah, sure. Well, let's start with GRL WEEP first. Normally, when you think about a project where dynamic testing is specified, the first question really becomes, okay, what hammer should the contractor use? You've got let's say an H pile driven to rock. It's 40 foot long. You need to prove 500 kips, right? What hammer should that contractor bring out that will, one, be able to drive the pile down to bedrock, be able to mobilize the required capacity, and drive it safely without damaging? Okay, that's really what it comes down to. So wave equation analysis it's a numerical analysis where you input various information, that is pile characteristics, size, length, the hammer model that you want to use, and also some initial thought of what the soil resistance looks like. What is it mostly friction? Is it end bearing? How is the friction distributed? And so then when you input all this information, the WEEP analysis performs the analysis, and basically you get an output that relates various information to the required capacity. For example, if it's a diesel hammer, the resulting stroke, pile driving stresses, again, both compression and tension. And also, obviously the most important thing, which is the blow count required to mobilize that capacity that you're looking for. So if you plug in a relatively small hammer, and the analysis says, okay, you need 350 blows a foot to mobilize your required capacity, well, that tells you your hammer is too small. Okay. So, you run this analysis, you give the results to the client, and he decides, well, all right, well, maybe the hammer's good, it's suitable, maybe it's not. Contractor, give me a larger hammer. And the other end of the spectrum, of course, is maybe the hammer's too big and the computed stresses are too large.
Okay,
which
okay.
can increase the risk of damage. So then, a smaller hammer. So again, the program is just meant initially to determine, hey, do you have a good choice hammer for your pile size and your required capacity?
Okay, so that's what GRL weep is hammer sizing. So we're not 350 blows a foot and we're not 10 blows a foot, right? And so somewhere in there, there's a sweet spot.
There's a sweet spot, right?
50 or 100, somewhere in there, don't you think? Blows
Most,
foot?
yeah, well, most DOTs like to see a blow count of somewhere between 3 and 8 blows an inch. If we're going to end bearing, we count blows per inches. So that's kind of like a good intermediate sweet spot there. So that's weep. CAPWAP, on the other hand, is a program that is similar to weep in some respect. It's a numerical analysis, but CAPWAP is used later. Once you go out and you run your dynamic test, you get your force and your velocity data, test your pile. Then what you do is you look at a specific impact, typically at the end of the driving. That's obviously where things are important, where hopefully the capacity is achieved. You take that data and then you do kind of a numerical signal matching process, similar to a wave equation analysis, where you're trying to actually determine now the soil unknowns. Okay. By the time you get to CAPWAP, you know your hammer, your hammer performance. You measured the performance in the field. Your pile length and whatever size. The only thing that's left is the unknowns is the soil. How much friction, how much end bearing. Okay. So it becomes a matching process. It uses those force and velocity measurements then to determine your soil solution, which includes your total capacity and its distribution, friction and bearing.
So with that, you've got tools for the drilled shafts. We've touched on the thermal integrity profiling, and I know there's a graphic that shows how that works, and I'm trying to understand that a little bit better.
Yes. Well, thermal integrity profiling is it's a method of integrity evaluation of a drilled shaft, and it utilizes the heat generated by the curing of the concrete mainly to evaluate the integrity of the drilled shaft. It can also be used for auger cast in place piles, micro piles, and other concrete foundations such as mass pours, for example. The test uses what we call these thermal wire cables. They are attached to the reinforcing cage, just basically with zip ties, and you use several of these cables based on the diameter of the shaft, and these cables have thermal sensors about a foot apart. So if you have, for example, a 4-foot diameter shaft, you'll have 4 of these wires, opposite each other, equidistant away from each other. And so what you're doing is during hydration, as that temperature increases, you're just basically measuring the temperature at each node of each wire every foot. And then the temperature data can actually these days, with technology, the data in real time can be sent to the cloud, where an engineer in the office can in real time check these evaluate or check these temperatures, make sure everything's working properly. And then typically after anywhere from, say, 15 to 30 hours or so, once the hydration has reached peak temperatures, the analysis can be performed. So how does it work? Well, basically the hydration allows you, as I mentioned, the interpretation of the as-built shape of the shaft, and it can indicate, for example, a necking in the shaft or solar inclusions in areas where you get colder than average temperatures. So, for example, if you had a solar inclusion that came in on the side of the shaft, it's possible that one of these sensors would be in soil, for example. So the temperature of that sensor at that location would never go above the soil temperature, which is 60 degrees or so, where the other nodes would go up to, say, 110, 120 degrees. So wherever you have colder temperatures relative to the average, that may show that maybe there's a neck or a soil inclusion there. Of course, if you have warmer than normal average temperatures, then that may indicate a bulge in the shaft, where the concrete, where the diameter actually increases. Testing can also show variations of concrete cover, just the general shape of the shaft, and also cage alignment, which is also very important.
Right. Excellent. No,
So that's the way it works, and like I said, it's done in real time. Data is just sent to the cloud as soon as curing begins, and then typically within 24 hours, you can send the results back to the client.
Well, that's beautiful, because you're demystifying the drilled shafts, of which is ideal if we're using more of them. And then there's another innovative technique, the bidirectional static load testing, and I'm not sure I understand that at all. Is that helpful tool as well?
Very much so. Traditionally a static test was done from the top, right? You build your frame and you use a hydraulic jack that sits on top of a shaft that then reacts up against a beam, and that allows you to apply a load to your shaft. You can measure your displacement, come up with a capacity versus displacement relationship. Well, about, 20 years ago, the industry came up with this a different way of loading the shaft. What they did is they basically moved the hydraulic jack from the top of the shaft down to some depth in the middle of the shaft. Depending on the type of soil, depending on if you're on bedrock, that information then is used. Where do you place the jack? Obviously, if the shaft is bearing on bedrock and it's all end bearing, then more than likely you would put the jack at the base of the shaft. If it's all friction with very little end bearing, then that jack probably would be more towards the center or a little bit below the center of the shaft. So the way it works then is you pressurize this jack, and so then the load is applied basically upwards and downwards at the same time. So that the resistance of the upper section is from the friction of the upper section, where the resistance of the lower section is the friction and whatever end bearing component you may have. So you're really applying the load internally within the shaft. You're actually braking the shaft, right? You're pushing the shaft, the shaft up and down at the same time. In some ways, that test is cheaper. It depends. It can be more expensive cost-wise anyway. But it does give you more information. For example, you could use strain gauges that can be attached to the reinforcing cage at specific levels, and then you can measure the strains as you load the shaft at those levels, and that actually also gives you the distribution of the resistance versus depth, not just the total.
So it's measuring the movement of the rebar cage versus the concrete in the shaft. Is that where the strain gauge is picking up?
It's actually, we're actually measuring obviously the load, but we're also measuring the displacement at various places, at the top of the jack, at the bottom of the jack, and also at the top of the shaft. You use some displacement transducers. So we're measuring, when you do a top load test, you're just basically measuring the displacement at the top of the pile. Here, we're measuring displacement at various locations of the shaft. And that allows us to evaluate then, the frictional resistance above and the resistance and the end bearing below the jack.
The fact that we can have strain gauges and transducers that are wireless and these new technologies pushing things to the cloud and having real-time information, and the shape and the squid, I imagine, lend themselves to that type of use of the data as well.
Well, yeah, we talked a little bit about these two tests. Both tests, first of all, can be done with an engineer in the field or remotely. These days, we have the tablets that are used out there have the capability to connect to through Wi-Fi, and an engineer is actually able to operate the equipment from his office, if you can believe that. We do the same thing with dynamic testing, for example. Probably 10% of our jobs that we do, I'm sitting in my office, nice and warm and cozy, and operating the unit from my office, actually. Pretty cool, really. Yeah, so, and we talked a little already about it with the drill shaft industry. These new methods, shape and squid, have brought the industry a long way. To be able to have a good feeling that the shaft is drilled properly at the right angle, that there is no necking, and to have good quality control, knowing that the bottom of the shaft is absolutely clean, before you fill it with concrete. Very, very useful information for the drill shaft industry. Like I said, 10, 15 years ago, I knew a few engineers that admitted to me, no way will I use a drill shaft. I don't have enough faith in it.
Right. I remember
it's
that.
a totally different view now. Totally different view.
Yeah, we didn't like it as installers either. It just seemed like too much. It seemed like too much work, too much material, and too much uncertainty. And thank you for the work you're doing, improving that.
And I think like everything else in life, I guess there's good installers and bad installers. I hate to say that, but we've done enough of these tests on drilled shaft to conclude or realize that what, there's drilling contractors out there who know what they're doing, but unfortunately there's some that need a bit more experience, and that's where the potential issues arise. And these test methods, of course, help in that respect.
Well, that's what the goal of this Pile Buck podcast is, Michael. Michael Morgano, I really appreciate your time today, of GRL Engineers. You've been there for 3 decades leading the branch, and I know now you're in a leadership role, guiding the teams and future inventions. And thank you for the really what GRL started doing and continues to do, which is bringing good science to engineering and to the benefit of the contractors and the owners. We've got a lot of infrastructure here in the United States of America that we need to rebuild, and it's hard work. We need young, talented people to be interested in it. And there's the driven pile and the drilled shaft is the primary elements when we're talking about heavy structures. And
for sure. I guess I'd like to add, I really personally feel lucky. I went to college, and when I graduated, it was time to get a job. And I remember my first interview with Frank, and basically he looked at me and said, "You like to travel?"
Yeah.
Being young and single, I said, "Heck yeah, I like to travel." He goes, "Good, you got the job."
Yeah, there you go.
So I guess I'm one of the lucky engineers where I was involved in the process of growing with a young company, a company that had this idea at the beginning, almost 50 years ago, that turned into when you look at it globally, it's probably billions of dollars industry when you think about it. Sometimes you go to college and you do things there, and you can't help thinking to yourself, is this ever going to turn into anything, right? And to be part of the story, part of our company here, to see the company grow from an idea to a global industry, it's really special. And that's why I'm still here 37 years later.
Well, let's talk about it again, Michael. I think it is a beautiful story, and you continue to add good science to the construction process. So thank you again, and keep building. Thank you.
Absolutely. And thank you again for the opportunity.